is able to follow along. So basically, first of all, kind of a schedule of the recitation sessions. So today we're going to introduce Xfoil. Next Friday is going to be the Friday before the quiz, right? So for the week of the quiz, there is no class on Monday because Monday was it's going to be a holiday. So basically, immediately before the quiz was the Friday. So our TA is going to come over here and talk through all the previous homework assignments, right? And basically the quiz is going to cover same materials as the what's covered by the homework assignments. So the TA is going to talk over this, and then the Friday of the quiz, Professor Drayler, who is the author of Xfoil, we are going to be teaching today, and also the author of AVL, which we introduced previous weeks, is going to come here and explain more about the Xfoil, but more on the viscous part. So today we are only going to be touching the Inviscid calculation. Basically, what we have been talking so far, right, is assuming all the vortices lie on the surface of the airfoils. There is no boundary layers, there is no flow separation, and so this is the first mode of Xfoil. It's Inviscid calculations, what we are going to be going through today, and that is very good in predicting lift and the moments of airfoils at high Reynolds numbers, which means large scale, faster speed, and at moderate angle of attack. So Professor Drayler is going to come along and discuss more on modeling airfoils with viscous effects, which is now really starting to predict the drag and stall of airfoils. So first of all, let me see what difficulty do you have in installing the software. I mean, either one is going to be okay. Either you have Xfoil or Mfoil. It's going to work pretty much the same for the purpose of this lecture. Anybody needs help? Yes? Okay, so if you're on, don't download the source. Don't download the source code of Xfoil. So go to download the executable. So so if you see like for Unix and Windows, it means it's the source code. If you can just download the Windows only, that'll be something you don't have to compile to be able to run. So, yes. Anybody else could do some help? I see Xfoil open. Okay, good. Okay, so if you open Xfoil or Mfoil, Xfoil, you're gonna get to a command line. So if I type Xfoil.exe, so you get to this black screen with a bunch of menu options, right? So the first thing we're going to try is a thin and symmetric airfoil. And to do that, you type NACA 0012. So NACA space 0012. And in Mfoil, the airfoil in the NACA portion, you type 0012. And if you can refresh this by clicking run, Mfoil is going to run. And for Xfoil, after typing NACA 0012, you type OPR, same thing as we were doing in AVL, and type alpha 0. And alpha with ALFA 0. So that should get you a plot similar to what you get in Mfoil. So this is what you get in Xfoil, this is what you get in Mfoil. right? Yes, that's good. Yeah, that's good. That's the plot I also got. It's the same one. So everybody go to the same location. Yeah, enter. Yeah, enter. Yeah. Oh yeah. Okay. So then alpha. Zero space zero. Oh. That's okay.
I don't know why you use Alex.
Small mouse right now.
You just have like a person that did
How did that even,
Xfoil.
So alpha 0 basically specifies the angle of attack at 0, right? So basically what we get right now is the pressure distribution, is the pressure coefficient distribution on this airfoil. And again, like what we said in class, the lower side is higher pressure coefficient, right? The bottom of the scale is 1.0. And the horizontal line is 0, and the further up you go, the smaller the pressure coefficient is. And the negative pressure coefficient is correlated with positive speed. So, and the pressure coefficient is actually defined purposefully so that a pressure coefficient equal to 1 means a speed of what? Just remember, 0, right? So Cp equal to 1, the bottom is 0 speed. So that should correspond exactly to the leading edge, right? If you look at the x location of pressure coefficient equal to 1, that's the stagnation point at leading edge with velocity equal to 0. And the minimum pressure is slightly more than minus 0.5, right? And again, like a 0 pressure coefficient means velocity the same as free stream. So can somebody do a little bit of calculation in their mind using Bernoulli's and tell me a pressure coefficient of minus 0.5 is a velocity how many times the free stream? Okay, remember how the calculation goes, right? So half is it 2? Not really, not as fast.
Is it 1/2?
Oh wait.
Still not as fast. So okay.
Oh wait.
So
is it 1/√2?
1 over root 2.
Or no, root.
Equal to a constant, which is the free stream, right? Which is basically, let's say if the free stream pressure is P infinity, then we have half of rho U infinity square plus P infinity, right? Okay, sorry for those who are P infinity. Okay, so the Cp is defined as P minus P infinity divided by half of rho U infinity squared, right? So okay, so if this is equal to minus 0.5, that means P is equal to P infinity minus, let me just write it as half times half of rho U infinity squared, right? Okay? I mean, I put this as half and half, but not as a quarter, because this is going to be used as a blob when we are plugging in that. So this is P infinity, right? And we know that P infinity is actually equal to. Let me just write it down the whole thing. So P minus P infinity is equal to the negative of half rho U squared minus half rho infinity squared, right? So this is basically equal to the half of the difference between this and this, right? So whenever you have pressure, I actually moved this around, sorry. So this is minus this is equal to minus of this, right? So Do you agree? Right. So this is basically from the definition of CP. So P minus P infinity is equal to that. And then the difference between pressure is the negative of the difference between the half of rho u squared, right? And that's equal to minus. I'll just copy this thing down. All right. Okay. So now we can combine this term with this term. What do you get? We get the half of rho u squared is equal to how many times? Half of rho u infinity squared. No. Yeah, 3/2. Okay, so it's equal to 1.5 times this much, which means the velocity is equal to how many times the u infinity squared? Like 1.2 something, right? Okay, so the velocity you get at the lowest pressure point, like what we usually call the peak suction, right? Suction means negative pressure. Peak suction means the peak of the negative pressure, which also means the peak of the velocity, right? In this case, it's about a little bit more than 20 times faster than the free stream. All right? Okay. Now let's put it at some angle of attack. So instead of alpha 0, let's make it, I'll still go to alpha 1. Okay, and in Mfoil, you make the angle of attack to be 1 degree and click run again. Okay, so you would get 2 lines instead of 1 line. So why do you get 2 lines? Because the airfoil has an upper surface, has a lower surface. And which one do you think corresponds to the upper surface? Which one to the lower surface? Well, that's another nice thing about having the pressure plotted backwards is the upper line corresponds to the upper surface, the lower line corresponds to the lower surface, right? Because the upper surface when the airfoil is generating lift, positive lift instead of downforce, then the upper surface is going to be sucking and the lower surface is pushing, right? So the upper surface has a lower pressure, which is higher on the negative CP plot, on the reversed CP plot. Okay, and take a moment to think about what is the function that describes the difference in the pressure between the upper and lower surfaces. Okay, it's a function that is pretty much 0 at the trailing edge, right? Just think about the gap. The gap is basically the distribution of lift, right? Basically, if you have a bigger gap, you have more lift at that chordwise location. It's pretty much 0 at trailing edge, goes bigger and bigger, and it peaks very close near the leading edge, right? I mean, it's the peak is actually not here because the pressure, the curve goes down further here, right? The peak is probably closer to the leading edge than the peak of the actual the peak suction, the peak of the pressure difference. And this is basically an approximation, or I should say, the function we saw in lecture today is an approximation of the pressure difference we see over here, right? Remember the effect of angle of attack. I can actually just load the decimals and try to visualize actually what it looks like. So this purple curve over here, compare this against I think, let me just use this one. Compare against not one of these blue curves, but the difference between the blue curves. Okay, they are actually the same function except for at the very leading edge, right? That corresponds to the problem with thin airfoil theory, right? Thin airfoil theory assumes the effect of the vortices are small compared to the free stream, which is of course not true at the leading edge because the combination of the vortices has to cancel exactly the free stream at the leading edge. So it's not small, which means the difference in the pressure is not going to go to infinity, okay, at the leading edge. All right. Okay, so essentially, this basically connects the thin airfoil theory to what we are looking at on the realistic airfoil, right? So basically, it tells you that what thin airfoil theory predicts is the effect of angle of attack actually reflects in how the pressure distribution changes as I increase the angle of attack, right? And imagine I take Mfoil or Xfoil and I want to make the angle of attack equal to 2. What I should expect is that the discrepancy or the difference between the upper and lower side should exactly double according to thin airfoil theory. Of course, it doesn't exactly double because of the effect of the sine. Okay, so thin airfoil theory approximates like sine of theta with theta, right? A tangent of theta also with theta, things like that. So it's not going to be exactly the case, but for 2 degrees, it's almost the case. And if you make it 3, the difference should be 3 times as large. And at some point, it should be pretty obvious that this function is actually the difference between the lower and upper surface is pretty. It looks like the one in the thin airfoil theory pretty well, right? Okay, any questions so far? No? Okay. Also look at the lift and see how different is the lift compared to what's predicted by thin airfoil theory. So at 3 degrees, the lift coefficient is 0.3624, right? Is that what you get also?
I get 3623.
It's pretty good. And according to thin airfoil theory, so you convert 3 degrees to radian by dividing 3 by 180 times pi, right? And then times another 2 pi. That actually gets you the lift coefficient predicted by thin airfoil theory. What I get is 0.389, right? 0.389 compared to 0.362. Okay, so that you get how much discrepancy there is between thin airfoil theory and this, which is less than 8%. Let me see. So this is what I get, and if I subtract this with 3289. Okay, if I just divide the whole thing by 0.32, it's, wait, something's wrong. This is 0.362, sorry, 0.3, what? 362, right? It's about 10% difference in the lift coefficient. Is that what you also got?
It's not that bad. It's like close.
It's close. Okay.
It's like ballpark.
Yeah, and our airfoil is actually 12% thick. Okay, 12% thick means the thickness. I mean, okay, so the last 2 digit of the NACA airfoil code is actually the thickness to chord ratio. So 12% thick, we get 10% error in lift coefficient. All right, so that's kind of gives you an idea of how much discrepancy you expect from the prediction of thin airfoil theory, right? Another thing that thin airfoil theory predicts is that for an airfoil without camber, the lift is exactly at the quarter chord, right? Remember, like when we look at the Desmos function, I just told you without proving that if you integrate this function times, so if you multiply this function by x and integrate it, then you divide the integral of the function. Okay, that basically computes the center of that function, right? You're gonna get a quarter. Okay, so which means if you integrate this function, right, a quarter minus x times g, you should get 0. Okay, which I do get 0. Okay, for the for the decimals, but 0 means the lift is gonna be exactly at the quarter chord. Now look at the either Xfoil or Mfoil. So Xfoil, I think let me just also get to the same point as you have. Alpha 3. Yeah, so the moment coefficient is going to be something negative, right? Do you remember for negative moment coefficient, is it a nose down or nose up moment? Nose down, right? Okay, and this is one way to explain this is that for thin Airfoil theory, there is a huge, although very tiny, there is a huge suction peak right at the leading edge, although a portion of the leading edge is going to be tiny, right? And for a realistic airfoil, the pressure kind of runs down. It's not going to go to infinity, right? So it does not have as much lift at the leading edge. Therefore, the center of lift shifts slightly downstream from the quarter chord. So can you calculate, based on what you get from Xfoil or Mfoil, exactly where the center of lift is from the lift coefficient and the moment coefficient? Right here, let me get this up. So what I saw here was CL is equal to 0.3624, CM is equal to minus 0.0042, right? Where is the center of lift? How far is it from the quarter chord? What? 26% from the leading edge, right? Not from the quarter chord. Okay, so how is the calculation done? The calculation is done by CM divided by CL, right? And you add it with a quarter. You subtract this from a quarter to get about 26%. So this is how much error we get from the thin Airfoil theory. Thin Airfoil theory predicts 25%, and in the real airfoil calculation, we get 26%. Okay, this also gives you a sense of the accuracy of thin Airfoil theory, how much you expect in this case. All right, any questions? Okay, so let's actually look at two different things. One is an airfoil that's even thicker to get you a sense of how much more error we can get. So instead of a NACA double 12, we enter NACA double 24. Okay, so it's going to be a pretty fat airfoil and something you expect not from airfoil used as a wing, but something used as a fairing to kind of make something more aerodynamic, right? So imagine you have a pillar or something. So you would see something, for example, like on Formula One cars, when they have this connection between the main part of the vehicle and the tires, right? Like things that sticks out, and you need some kind of fairing to actually reduce the resistance of these structural components. Now, if you look at this airfoil at also 3 degrees angle of attack, you see that CL becomes even larger, right? So CL used to be 0.362, now it's 0.396. So as we make the airfoil thicker, right, we get actually more and more lift. There is a increased error compared to the thin airfoil theory. And also, if you look at CM is minus 0.11 instead of minus 0.004. So the moment, the amount of error in the in the center of lift also increases, and this is probably going to be more than 27% of the chord, right? If you plug in the numbers to calculate. All right. Okay, so this is for a thicker airfoil. And the next thing we'll do is we'll make a cambered airfoil. So actually one of the most popular airfoils people use is NACA 2412. If you type NACA 2412, you get an airfoil that is probably one of the most common airfoils you would see. So what does the 4 digits mean? So how many people are familiar with what does the 4 digits of a NACA 4-digit airfoil actually means? Not many. Okay, so I already told you the last 2 digits represent a thickness to chord ratio, right? So we tried 0012, which means a 12% thickness to chord ratio. 0024 means double the thickness, right? You probably have seen on your screen that 0024 is twice as thick as 0012. So that's what it means. That's always what it means for the last 2 digits in a 4-digit airfoil. The first 2 digits actually means independent things. So for example, 2412, the 2 and 4 means 2 different things. The first number 2 means how much camber there is on the airfoil. So that's the D over C in your homework. Okay, so if you have looked at the question 2 of the homework. So for this airfoil, the D over C, D means like the at the maximum camber. By the way, camber is basically the midline between the upper and lower surface. That's what we call camber of an airfoil. Okay, so so that means the midline would deviate from the x-axis by a maximum of 2% of the chord. So not much, right? But 2% of a camber can already make a pretty significant difference aerodynamically. That's the first number. The second number 4 is the only number that's not in percent. Okay, so the first number 2 is in 2% of the chord. That's the max camber. The last 2 digits are percent of the chord in terms of the thickness. The second number is not percent, it's tenth. So 4 means 4/10 of the chord. What about 4/10 of the chord? That is where the maximum camber is. Okay, that's where the maximum camber is. And actually, if you want to get something close to what we have done in class today. So remember in class today, we looked at the thin airfoil theory for cambered airfoil by setting A0 back to 0 and A1 to some positive number. And the camber is a parabola, right? For parabola, where is the maximum camber? Right in the middle, right? How many tenths is right in the middle? 5, right? So for to get something similar to what we looked in class, which number would you change, and what would you change it to? Second number, you change the second number to 5, right? Instead of 2, 4, 12, you do 2, 5, 12. And if you run it again, and particularly if you set the angle of attack to 0, that would actually correspond to what we have ran today. And if you set the angle of attack to 0 and use 2, 5, 12 as the airfoil, you're going to get something more like this, right? And then if you look at the difference between the lower and the upper pressure and think about what we get in thin airfoil theory, like a semicircle or semi-ellipse, right? That's pretty much this pressure distribution. The gap over here, the gap is maximum in the middle, right? But it's not a sharp maximum. It's pretty flat. It means in this case, like flat means these two lines are pretty parallel in a pretty big portion in the middle, right? Means like the pressure difference between upper and lower surface stays roughly the same number for a large fraction of the chord. and this one should have a lift pretty close to the center. Now, according to thinner foil theory, the center of lift should be exactly at the half chord, right? Which means the Cm should be a what fraction of Cl? So if this guy has to be half, okay, if this is 50%, Cm needs to be a what fraction of Cl? A quarter, actually minus a quarter, right? Okay, now look at your screen. The Cl I get is 0.25, and the Cm I get is minus 0.066. Right? If you multiply 4 onto 0.066, it's 0.26-ish, right? So that's 0.25, 0.26-ish. So that's actually getting close to that CL.
What angle of attack?
Zero angle of attack.
Oh, okay.
Yeah, that's what we looked at in class today. That is, remember, like the A0 term corresponds to the angle of attack, right? I mean, if you shift the A0 to something else, then like the distribution is going to be a combination of the angle of attack term and the semi-elliptical term. So yeah, make angle of attack equal to 0. Then you get the semi-ellipse. All right. And I would say you would probably get like a 45-ish% chord as the center of lift for this airfoil, right? Like it's pretty close to what thin airfoil theory tells you. And let's get back to our popular airfoil 2412, and you would imagine it's going to be something between, right? So essentially, you're going to see that at 0 degrees angle of attack, the maximum gap between the upper and lower surface is going to shift towards the leading edge a little bit, right? So it's you get a shape pretty much like this. Okay, and the critical thing is that even for that airfoil, if you increase the angle of attack, and if you just remember what the previous shape is and how the shape has changed, you should see that the difference in the shape as you increase the angle of attack is going to be exactly that angle of attack function. Okay, so that can be seen in Xfoil a little bit better, because Xfoil you can type ASEQ, ASEQ. That's like an angle of attack sequence. Okay, and if you start, I don't think I put the NACA airfoil yet. 1 second. NACA upper and ASEQ, and it'll ask you to enter the first angle of attack. Let's say put it at 0, and the last angle of attack, let's say 4, and the increment, let's say 2, right? So you should get a curve like that.
How'd
You get
you
it?
plot multiple?
Multiple what?
How'd you get like overlaying them again?
Oh, ASEQ, ASEQ, like a sequence of alphas. That means like alpha sequence. So in the same place where you would enter alpha 0 or alpha 3, you enter ASEQ. And then it is going to ask you to enter the first alpha, last alpha, and the increment. So I enter the 0 as my first, the 4 as my last, the 2 as my increment. So I should get 3 different distributions overlapping with each other, right? So what you see is that even for non-symmetric airfoil, the difference in the CL, okay, so the 3 group on the upper side is the upper surface, the 3 ones on the lower side is the lower surface. The difference between adjacent angle of attacks, both for the upper surface and lower surface, is similar to the angle of attack function. All right. Make sense? All right. Okay, so here's a challenge. You know how to manipulate the 4 digits, right? Try to come up with an airfoil where the center of lift is at the leading edge, or as close to the leading edge as possible. At least the upstream of the quarter chord. All right. You can change the 4 digits whatever you want. Remember, the first digit is the camber, is the magnitude of the camber in percent. The second number is the location of the max camber. It can be 1, meaning the max camber is very close to leading edge. It can be 9, which means it's very close to trailing edge, right? The last 2 digits are how thick the airfoil is.
We can change alpha or?
Yeah, you can change alpha to whatever you want. You can make it positive lift or negative lift or whatever you want, right? Because negative lift just means you're flipping the airfoil around, right? Like the knockout 4 digit doesn't allow you to have negative camber, but you can just flip it around, which means you want a positive camber airfoil to generate that negative lift.
Yeah.
That must be a camber location closer to the leading edge, right? So here, you can see your max camber, right? It's close to here. So I would guess your second digit is 9 or something. Is it all clear? How do you know if you succeed? Right, just to look at combination of CM and CL, right? So that's the equation that tells you where the center of lift is. Oh.
Playing around a little bit. It's interesting.
Where do you think the center of lift is?
Well, if we take CM over CL, right, we're adding onto the 1/4.
Yeah.
So it would actually, we're going the wrong direction.
Yeah, it's actually downstream of the half chord.
So it's actually the center lift's right at the very back in this case.
At the very back. So you divide this by this, you get like about like 1/3 or something?
Yeah, about
less than 1/3.
Yeah.
Right.
So center lift is
Yeah, it's somewhere.
right. So it actually, it's the opposite.
Okay.
Yeah. I want to flip this, like, but it only allows between -90 and 90.
You want to flip which one? The angle of attack or what?
This is like this thing I want to flip.
Oh yeah, so yeah, for the airfoil it doesn't allow you to have a negative camber, but you can actually make it that you can just reorient yourself, right? Think about this direction as the upward direction. So you basically just want this airfoil to generate negative lift. Make sense? If you put it at, let's say, -5-degree angle of attack, right? It's going to be generating negative lift. Yes,
Oh, okay,
CL is
then.
already negative.
Okay.
close to zero as possible.
I got like 11.
Oh, nice.
There has to be a pathway.
Yeah, it's minus, and your CM is there.
I have on some distributions. Yeah. Monte Carlo.
As long as
Manual Monte
your
Carlo.
CM is negative, the CL is positive, it's gonna be down.
You want the value that is generated by your fraction to be positive.
No,
You compute where your center flipped is.
But I don't know how to get there either.
but I just don't, I'm not seeing.
I hate when that happens.
It's not close yet.
Maybe we can't get CM to be positive, but we can get both things to stay like this.
Oh my gosh.
But it's not zero.
It's very close, right?
My CL is so,
So,
it's not worth trying.
yeah, so we actually get the solution already. It's actually there is a trick part of the question in it. It's because if you have a positive camber, no knockoff 4-digit airfoil is actually going to get you my answer. You actually have to flip it. And the right way to flip it in this setting is you want it to generate negative lift. Okay, so just now try to think in the context of generating negative lift and see if you can get a lift right at the leading edge. If you already got it, you're free to leave. No, you can put a negative camber. So the camber is always going to be positive, but you can just flip it around, right? So if you ask a positive camber airfoil to generate negative lift, it's the same as just flying backwards.
And then the normal attack, the induced thrust from
Oh, okay, so you're going to be doing something, just knock out double top, right? And if you go to operating condition, if you type
just set it as an
alpha,
angle attack.
let's see, minus one,
Very firm.
what do you get?
How big of a negative angle?
Right?
Yeah. Negative 50.
You're getting,
Oh,
you're getting
You can
negative.
theory
It's
go.
like, when I see this working.
You can go as high as you want.
Oh. This is like a
Yeah, now somebody get a negative CL, right? But the lift is still close to the quarter chord. It's upstream of the quarter chord already, but still close. How do you make it go towards the leading edge? I'm from minus 50. Okay, I shouldn't look. Okay.
I think it's pretty, like, almost at
Oh,
I
this
can
is
get that.
yeah, this is almost precisely at the leading edge. Good job. Yeah, so you see what you get, right? You get lift over here, well, negative lift over here, but positive lift over here.
Mhm.
So it's almost like you get a horizontal tail, right?
Like,
So if you flip it backwards,
yeah.
this part is creating lift, this part is creating downforce.
Oh.
Right? It's cool, right?
Yeah.
Yeah. Yes. It's okay. Yes. So this is already you are now upstream of the quarter chord already, right? Because you are going to be subtracting the ratio between the negative and the negative. But if you calculate where it is, it's not at the leading edge yet. So if you divide this by this, right? Yeah.
Question.
Yeah.
So like this.
Nice. It's very close, right? I mean, this is actually you're getting the lift upstream of the leading edge.
Yeah.
You see? Right. So somebody found the interesting thing is that the center of lift can be outside of the airfoil, right? How? This is this is Hull. So if you see the pressure curve flips over somewhere in the middle, that's actually Hull, right? So if you think about backwards, then the leading edge portion is creating lift, but the trailing edge portion is actually creating downforce. So it's almost like you have a horizontal tail, kind of pushing the airplane to make it jump. And for some of you who have a very negative angle of attack and make the angle of attack closer to 0, that's going to have this switching effect coming. Yeah, if you have a very negative angle of attack, you're going to find out that making the angle of attack closer to 0 but still negative is going to help move the center of lift closer to the leading edge. Yes?
Yeah, I think I have something that fits, but I'm having a bit of trouble understanding like physical the graph. Can I say this?
Yeah, this is very close, right? So yeah, the CP graph means the following. 1 means a stagnation point.
Yeah,
right.
I think it's the fact that there's like 1 here, but also
The one that worked for me was
here, like this.
It gets it exactly.
This section is like
it's very negative 3.5.
because I'm not understanding the
To the quarter
in the beginning when
Yes,
it first
it's because the division of CM
Yes.
divided by CL is like 1, 2, 3.
Let's see what is the best way to explain it. So this is at a negative angle of attack, right?
Yeah.
So the flow comes from up here. And the stagnation point, you think
Negative
is where?
3.
Is it on the upper side? Or it's going to be on the upper side, right? And that corresponds
That's like a
to
third.
the Mfoil,
Or half.
you see the airflow is slightly longer than this range, so it doesn't look very good, but this point should correspond to somewhere here. Okay. And now because the flow goes like this, and the flow has to go around, the fastest flow actually lies almost exactly at the same location of the stagnation point, but on the other side. That's what this is.
Oh,
This is
okay.
like, this is slow
Direct.
zero velocity. This is fastest flow, which is almost at the same location,
Well,
but on the other
actually-
side.
So, yeah.
Okay. Yeah.
Negative 3.81.
So basically, like from here to here, it's gonna be like slow velocity, but it's gonna at the opposite side of the 0 point, it's gonna be the fastest.
Yes.
So it's like gonna be
Actually, no, it's actually
Exactly. Yes. Yeah. So over this portion, the upper side is slower than the lower
Gen
side.
Ed.
So the upper side is gonna have a higher
You
rate.
always think it's kind of deeper.
Lower side.
No,
Now
like
starting from here,
Harvard. The Harvard. You
this
go to
is
Harvard.
flipping.
Yeah,
It
so like,
starts to
I
flip
was
over
like,
here.
I also go to Harvard.
Do you actually?
Yeah.
I mean, there is a
like
slight
goes back up.
Yeah,
That's
this goes
crazy.
back
I
up.
actually didn't know
But
this.
over
Why
this
did you-
portion, it
I thought you went
flips
17.
over. The lower side is now slower than the upper.
No, I go to Harvard.
Slightly slower because they're almost the
How do you
same.
make it on time every day?
I run.
Oh, that's fair.
This is how you interpret the
Anywho, but yeah, I'd like
Sure.
the requirements
Any other questions? Yeah.
class.
Yeah, so if the ratio, if both numbers are the same sign, which right now is 1, and the CM is about a quarter of CL, then you're right at the end. So think about that formula, right? Yeah. So here you probably want to make the angle of attack lower. So because right now your problem is low. So
I'm in the quad.
they are not the same size. Your CL is in
Wait,
net.
really? I live in Winthrop House.
So let's say
Oh, I
no,
let's see the quad.
make it even more negative.
Why would you be in the
Yeah,
quad a lot?
because
I have friends there.
right now they are the same size. But now CL
I've never
is
actually
too
seen it
negative. So make it like
You go to Pinocchio's.
Oh, that's fair. I've been there for sure. That's crazy.
Now it's
Pinocchio's hits
actually
different.
What kind of costume are
right.
you
So your CL needs to be
Yeah,
slightly like a 4.5 or something.
I'm
So then it's
I am as well.
Really?
So I actually have no idea how I've never seen it before.
It's crazy.
nice.
What classes are you in?
Yeah.
What classes are you in?
I'm in like 225.
Oh, I've heard of this.
So cool. But it's applied. It's like